I am in Golden Gate Park, this beautiful green oasis here in San Francisco, but this location has not always been a park. It was actually great big sand dunes, and with the help of this structure behind me, a windmill, the city was able to pump water from the aquifer 200 feet below and use to irrigate this area to make it into a park. And so this is an example of the primitive methods of getting water out of aquifers. We do the same thing today, but much bigger, fancier, and more technological advanced equipment, but the idea is the same. If we don't have enough surface water on our earth from runoff, we take it out of aquifers. So let's learn a little bit about groundwater and aquifers.
Let's start with a couple surprising facts. Okay, did you know there's more water underground than in all the lakes and streams on the Earth's surface? In fact, underground aquifers hold 99% of all liquid fresh water. The rest is in lakes, rivers, and streams. Groundwater is found in the pores of soil, sediment, and rocks. And groundwater provides 50% of all drinking water in the United States. And in a typical year here in California, provides 36% of all of our water. Now are you interested? In this video, we'll cover porosity and permeability, which are important characteristics for soil and rock and sediment to hold water. We'll cover what an aquifer is, which is the rock that stores the water. What happens if too much water is withdrawn from wells from the groundwater aquifer. Then we'll talk about groundwater contamination, and then some of the laws, both state and federal, about how our drinking water is protected. Now, groundwater and surface water are essentially one resource. They're physically connected by the hydrologic cycle, in which water evaporates, forms clouds, falls down to the Earth's surface as rain or snow, and then some of this precipitation seeps into the ground, moving slowly into an underground aquifer, eventually becoming groundwater. So water laws and water policies often consider groundwater and surface water as separate resources, but they are really functionally independent and part of one cycle. When you turn on your faucet, where does that water come from? Well, that depends where you live. Some cities or municipalities have their own local watershed, such as Marin County here in the Bay Area, which has 6 large reservoirs that runoff flows into from the watershed, which is Mount Tam. Other counties rely on surface water brought far away from major reservoirs that are replenished by snowmelt. Others may rely completely on tapping into groundwater. In fact, many municipal, agricultural, and disadvantaged communities rely on groundwater for up to 100% of their water supply. So there are 3 main factors that determine whether a source of groundwater will be a viable resource for a community. One is the quantity of it. Is there enough groundwater to supply the community above it? How easy is it to withdraw or pump from that aquifer? How deep is it? How expensive is it to get to? And number 3, what's the water quality like? Are there pollutants that affect its drinkability from nearby sources of pollutants? Earth materials vary widely in their ability to both store and transmit groundwater. Furthermore, not all sediment or rocks can store water. There are 2 important qualities that are necessary for rocks or sediment to hold water, and they're porosity and permeability. Since water is stored between the individual grains within a rock or unconsolidated or loose sediment, the sediment or rock has to have a significant amount of empty space to hold the water. This empty space is called pore space. And porosity is the proportion of the material that is made up of these voids or these empty spaces. For example, if half of the total volume of the rock is pore space, the porosity is 50%. Coincidentally, this is the same quality of a rock or sediment that makes it a good reservoir to hold oil or gas. And a typical sandstone, for example, has a porosity of 30 to 40%. But it can vary widely, and that's based on 2 qualities of the sediment and rock. First is, how tightly are the grains packed? In a more tightly packed or compacted rock or sediment, the lower the porosity. If the grains are, or the rock is more loosely packed, then porosity would be higher. The second quality that determines the porosity of a rock or sediment is how similar are the grain sizes, and this is called sorting. If the grains are a very similar size, meaning they're well sorted, then the porosity is greater. If the grains are a varying size, which would be considered poorly sorted, the smaller ones can fit into the spaces between the larger one, and that reduces the porosity. The second quality that determines whether rock or sediment would be a good place to store water is its permeability, which is the ability of earth materials to transmit, not store, but transmit the groundwater. And this varies by orders of magnitude, and it's determined by the size, the shape, but mostly how interconnected are those pore spaces. So connections between the pore spaces are wider in coarse grain materials such as gravel than in fine grain materials such as sand. And another more technical word for this is hydraulic conductivity, which is just a measure of how easily water can pass through rock or soil. In general, porosity and permeability go hand in hand, but not always. There are some unusual circumstances where you can have high porosity, but not necessarily high permeability. Rainwater soaks into the ground, percolating down until all the pore spaces are filled. The rock or sediment layer that holds this water is called an aquifer. And as you can imagine, good aquifers have high porosity and high permeability. The water will infiltrate down until it hits a low permeability or impermeable layer such as clay, and then it begins to pond above this layer, which is called an aquitard. When the percolating water completely fills in the pore spaces of the material, it creates a saturated zone. This is the area that serves as potential groundwater storage. And the top of this saturated zone is called the water table. The area above the water table makes up the unsaturated zone or zone of variation. And in this upper zone, the spaces between the particles or the cracks in the rocks contain both air and water, but is not completely saturated. And keep in mind, the water table is not a static level. When it rains, the water table gets recharged and rises in the subsurface, and when groundwater is withdrawn from the aquifer, the water table can lower. It's a bit of an oversimplification to say that water ponds to make up the saturated zone, because water moves horizontally within the aquifer and vertically. It flows due to differences in elevation of the water table and water pressure. So it moves from areas of higher pressure to areas of lower pressure. One way to talk about pressure is through the concept of hydraulic head, which can be visualized as the height of the water table. The water will flow towards where the water table is lowest. Velocities of groundwater flow are generally low and are orders of magnitude less than stream flows. Typical streams flow about 7 miles an hour. A slow river can flow about 3, a rapid one about 5 miles an hour. But groundwater, on the other hand, can flow as fast as 1 foot per day, but as slow as 1 foot per year or decade. It's extremely variable, but by any measure, it's way slower than surface water. And these low velocities of groundwater flow can have really important implications, particularly in relation to the movements of contaminants that move with the groundwater. Let's now shift our focus a bit to where groundwater is more used. In areas where water demand is greater than runoff, we look to our underground storage system, the aquifer, to meet this demand. This map shows the average rainfall throughout the United States, but what this doesn't account for is where demand is greatest, either due to population density or, more importantly, where irrigation demands are high due to agriculture. As you can see, this is the case for most of the United States where consumption is greater than precipitation. Certainly true for parts of the Midwest and in California, and especially in the Central Valley of California. This is due to agriculture in both cases. The Ogallala Aquifer is one of the world's largest aquifers, and it underlies 8 states in the Great Plains. 27% of the irrigated land in the United States overlies this aquifer and supplies about 30% of all groundwater used for irrigation in the United States. To say it's an important aquifer is an understatement, but due to growing agriculture demands, it's becoming depleted. It is not recharging as fast as the water is being pumped out of it. Clearly, we have been treating this as a non-renewable resource, and we can expect problems arising from this approach in the near future. When water continues to be pumped from an aquifer where demand outpaces replenishment, the result is groundwater overdraft and the water table declines. The water table will decline most dramatically near where it's being pumped and diminishes away from the well. As a consequence, a well will have to be drilled even deeper to access that groundwater supply. But the pattern of the lowering of the water table forms what's called a cone of depression, which is most severe at the site of overpumping. And this clearly shows that other people's water supplies is affected by their neighbors' actions. In other words, we all share a common aquifer, and what your neighbor does will affect your access to groundwater. Another consequence of overdrawing groundwater is subsidence, which is a gradual lowering, a settling of the ground surface. There are a few different causes of subsidence, but in some agriculture areas, such as the Great Valley, the cause is overpumping of groundwater. The groundwater actually helps support the overlying land surface, so when that gets pumped out, it removes some of the support. This is especially true when fine-grained rocks hold water and that gets removed. The rock compacts because the water is partly responsible for holding the ground up. And when the water is withdrawn, the rocks fall in on themselves. Parts of the San Joaquin Valley have subsided as much as 29 feet. Think about infrastructure damage, roads and buildings, and what this does to the area. A third, much more site-specific effect of groundwater overdraft is saltwater intrusion. In coastal areas, fresh water gets discharged towards the coast, and this prevents the landward encroachment of saline groundwater. If this balance is upset by too much water being removed from the aquifer due to pumping, then saline groundwater can migrate landward, and this is called saltwater intrusion. If a pumping well is close to that landward migration or migrating freshwater saltwater interface, the potential exists for saltwater contamination in the well. And since saltwater cannot be used to irrigate crops or consumed by people, saltwater intrusion can be really problematic in certain coastal communities that rely on fresh groundwater supplies for their livelihood. In the Pajaro Valley, just south of Santa Cruz, this is happening, and saltwater intrusion has moved inland about 3 miles from the coast since the 1950s.
For most of this video, we've talked about groundwater and how it gets stored and transmitted through aquifers, but I want to conclude with talking about what sort of legislation there is that protects both our surface water and our groundwater and keeps it flowing freely. Here in the United States, we take for granted our water supply, but what sort of legislation is there that protects our groundwater and our surface water? Well, it's kind of complicated. Here in California, we are one of only 2 states that does not regulate how much groundwater is taken out of our aquifer. Until recently, there have been no regulations about this. If you are a landowner, you basically have an unlimited right to the groundwater beneath your property. This is starting to change. In 2015, Governor Jerry Brown started instituting a plan to start regulating groundwater withdrawals, to monitor it, regulate it, and to make a sustainability plan. And basically, the legislation that he signed gave the rights to monitor groundwater to the individual water basins, kind of at a regional control, not at a state level. So areas that are impacted with groundwater withdrawals are starting to address how much is taken out and by whom and make a sustainability plan. Let's take a moment and examine some of the federal laws that protect our clean water. The first bit of legislation was passed in 1972, and this was the Clean Water Act. And basically this made it illegal to dump any contaminants or pollutants into the navigable waters of the United States. So your first question should be, what's a navigable water? Well, I had to look that up. That means any body of water that can be sailed upon by boats or ships. So from today's standards, this is a really weak piece of legislation because it only addressed surface water and not groundwater, which we know to be a very important water source. This 1972 legislation was amended in 1986 and then again in 1996 and ended up becoming the Safe Water Drinking Act. And this was a little bit different than the first legislation, that it addressed all water resources, including rivers, lakes, streams, and groundwater. And it established 90 different contaminants and set maximum containment levels for those contaminants. In general, these laws have worked very well. We have a very clean water supply in the United States, except for a couple isolated incidences. But I want to bring up one particular piece of legislation that is potentially very damaging to groundwater, and this is called the Halliburton loophole. It's probably surprising to many of you that oil and gas companies are the only industry that are allowed to inject potentially hazardous materials into areas that could potentially interact with groundwater. Oil companies are increasingly conducting hydraulic fracturing, which is a process in which they inject water, sand, and toxic chemicals into a well deep within the earth and fracture the rock, enabling oil and gas to be collected. And it's the drilling fluids that are potentially toxic. And they do not have to report what they put down into the drill holes to the EPA, nor does the EPA monitor it, nor do they divulge what the chemistry is. And the reason behind this is they say it's a proprietary recipe for their drilling fluids. So how did this legislation come to be, where oil companies are exempt from the EPA regulating what they put down into the subsurface near groundwater supplies? Well, it was in 2005 when the Bush-Cheney administration wrote the energy bill, and it exempt fracking from oversight of the EPA. And Dick Cheney was the CEO of Halliburton, which is a company that pioneered this technology to get fossil fuels out of a certain type of rock. And he knew this was going to be very lucrative and important part of energy recovery, and it was written into the energy policy. And therefore it's called the Halliburton loophole. And that is still in effect today.